Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. So this is a new problem that is going to give us kind of like a practice situation for recursion, right? So the problem says that there are n stones numbered from 1 to n. Okay, so there are n stones somewhere and you have numbered them from 1 to n, right? For each I, that is for each index, the height of the ith stone is hi. So for any ith stone, the height is given as hi. So for the fourth stone, the height might be given as h4, height might be given as h3, height might be given as h2, and so on, right? So on any ith index, if I draw here, on any ith index, the height of the ith stone is going to be given as hi. Okay, so height of the ith stone will be given as hi. Now post that it is given that there is a frog who initially is on stone number 1. So there is some frog who is sitting on stone number 1. Okay, he will repeat the following action with some number of times to reach the stone n. So frog is going to do some actions multiple number of times so that frog can reach the nth stone. This is the nth stone. Frog wants to reach from the first stone to nth stone. This is the journey that frog wants to do. Frog wants to go from first stone to nth stone in some operations. What are the operations available? If the frog is currently on stone I, that is if the frog is at any stone I, it can jump to I plus 1 or I plus 2th stone. That is, from any stone you can just jump to the next stone or the stone to next of it. So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different, and a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our System Design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video.
Next of it, that is I plus 1th stone or I plus 2th stone, right? If the frog is currently on stone I, it can jump to stone I plus 1 or stone I plus 2. So let me draw it here. From any ith stone, you can either go to the I plus 1th stone or you can go to the I plus 2th stone, right? Okay. Here, a cost of absolute of hi minus hj is incurred, where j is the stone to land on. So for example, if from the ith stone you went to the I plus 1th stone, then the cost that you have to bear is absolute value of hi minus hi plus 1. Why? Because you landed on hi plus 1. See, this is hi minus hj, where j is the stone that you land on. So if from I you jumped and you landed on I plus 1, then the cost will be h of I plus 1. Okay. And if you landed on I plus 2, then the cost will be hi minus hi plus 2. This is what they want to say, right? That is, if from the ith stone you took a jump and you landed on the jth stone, here j is I plus 2, then the cost will be hi minus hj, right? So cost of hi minus hj is incurred when j is the stone to land on. What you need to figure out is find the minimum possible total incurred, or I would say minimum possible total cost incurred before the frog reaches n, right? So what you have to figure out is that if the frog wants to go from the first stone to nth stone, considering that from any ith stone it can take a jump to I plus 1 or I plus 2, in what minimum cost the frog can reach from the first stone to the nth stone, right? You have to figure out the minimum possible cost to reach nth stone. Okay, minimum possible cost to reach the nth stone. For example, if let's say this is the given situation to you, here the first stone is of height 10, second is of height 20, second is of height 30, next is of height 40, next is of height 20. In this case, the answer is going to be 30, right? In this case, the answer is going to be 30. Why? Frog can take the first jump from, this is the first stone, second stone, third stone, fourth stone. So the first jump can be taken from first stone to second stone. So if I calculate the cost is equals to 0 plus h1 minus h2. What is h1 minus h2? Because h1 you started, h2 you landed. Absolute value. So 10 minus 30, absolute value is what? 20. Okay. So this value is what? 20. And then from the second stone, you can directly take a jump to the fourth stone. So I'll say plus h2 minus h4. What is h2 minus h4? h2 is 30, h4 is 20. 30 minus 20, absolute value is 10. So this is 10. So technically 20 plus 10 is 30. So this total cost becomes 30, right? So you have to figure out in what minimum possible cost the frog can reach from the first stone to the last stone. The frog will be making multiple jumps in between. You have to make sure that you take the most optimal jump. You can even see if you follow the path that we go from 1 to 2 and then 2 to 4, the total cost incurred will be, this is h1 minus h2 mod plus h2 minus h4 mod is equals to 30, right? This is the situation given to us. We don't need to care about any constraints for the time being, because for very big constraints, I would say there will be a new technique that you need to introduce here. But the overall agenda is you need to try to solve the problem recursively. How can we solve this problem recursively? Because this problem is going to give us a good perspective on how we can solve problems based on some previous set of problems. So if you have done some basic recursion already, right, based on whatever we have discussed on recursion, can you try to solve this problem? Now let's say if you want to figure out how can we solve this question, right, then think in these terms, that if you are at the ith index, for example, your frog is at the ith index, okay, from the ith index the frog can jump to the I plus 1th index, right, this jump the frog can take, or the frog can go to the I plus 2th index. See, frog can go to the I plus 2th index. These are the two possible jumps that the frog can take, right? One is here, one is here. These two possible jumps the frog can take, okay? Now, just think about it. If the frog starts from the first index, if the frog starts from the first index, from the first index it can go just to the second index or the third index. Can I say that? From the first index it can only go to the second and the third index, right? Okay. Now, if somehow you know, like you don't know how to get the minimum cost from 1 to n, right? This is something that I don't know. But somehow, if I know what is the minimum cost that the frog will take to go from 2 to n, let's say we already know minimum cost to go from 2 to n, right? Somehow we know this minimum cost. Somehow we already know this minimum cost, okay? And we already know the minimum cost to go from 3 to n. And let's say we also know this minimum cost, that what will be the minimum cost to reach from 3 to n. If let's say we already know these costs, let's say this cost is x, this minimum cost is x, this minimum cost is y. If I already know that in x cost, in x minimum cost, you can go from 2 to n, or in y minimum cost, you can go from 3 to n. Let's say if I already know this, then can I say that? Then we can very easily calculate the cost from 1 to 2, 1 to 3, and see the best answer. Can I say that? Right. So if you already know this cost, my answer is going to be what? If I take a jump from 1 to 2, the cost will be h1 minus h2 plus x, because you went from 1 to 2 and from 2 you went to n somehow in the minimum cost x. From 2 you went to n somehow with the minimum cost x, and h1 minus h2 is the cost to go from 1 to 2. If you go from 1 to 3, minimum cost, like cost to go from 1 to 3 is h1 minus h3 plus y. Y is the minimum cost to go from 3 to n. So technically you are saying in the first approach you are going via 2, in the second approach you are going via 3, right? That if I want to reach from 1 to n via 2, if I want to reach 1 to n via 3, this is going to be the approach. This is going to be the approach, right? So what will be my suitable approach? My suitable approach is going to be minimum of, I can say, x plus h1 minus h2 comma y plus h1 minus h3. Okay, we are going to take this, right? That now if we go via 2, what is the cost? If we go via 3, what is the cost? Just take the minimum out of it. Just take the minimum out of it, and that's it, right? And you can look at this in these terms also. You can look the same thing in reverse order also. Nothing much will change, but I want to still explain in both the terms. Okay. If you see, this is the first stone, this is the nth stone, right? Now just think about it. If finally the frog wants to come at the nth stone, can I say the frog can come to the nth stone from the n minus 1th stone or n minus 2th stone? Can I say that? These are the two stones from which the frog can come. N minus 1th stone or n minus 2th stone. Like only these two stones are there which can directly land you at n. I can say that, right? Only these two stones are there which can directly land you to n. No other stone will be able to directly land you to n, right? There can be a case that from n minus 2, instead of just directly going to n, you went to n minus 1. Then that, I would say, solution will be counted as the solution for n minus 1 only, okay? So I'm saying one more way to look at the problem is for reaching n as the last stone, only n minus 1 or n minus 2 can be the second last, right? Only n minus 1 and n minus 2 can be the second last. So if somehow you know what is the minimum cost to reach from 1 to n minus 1, if we know minimum cost to reach 1 to n minus 1 as x and 1 to n minus 2 as y, that is, you also know what is the minimum cost to reach from 1 to n minus 2, that is y, right? You know both of these minimum costs. So we can say that if you are going from n minus 1 to n, then the cost involved will be what? The cost to take the frog from 1 to, this is n minus 1, right? So this should be x. This is x, this is y. Okay. So the cost to take frog from 1 to n minus 1 was x plus h of n minus 1 plus h of n. This will be the cost incurred if you reach n via n minus 1. Reaching n via n minus 1. If you are reaching n via n minus 2, then I can say that if you want to reach from n minus 2 to n, then to reach n minus 2, first of all, the minimum cost is y. Minimum cost is y, right? To reach n minus 2. So y plus h of n minus 2 plus h of n, that is the cost of the jump from n minus 2 to n. These are the two ways, right, to reach n. So I can say my final answer is going to be what? Minimum of x plus hn minus 1. I guess this is minus hn, right? This is minus h of n, comma y plus hn minus 2 minus h of n, right? So these two cases, like we can visualize the same problem in any way, that if you already know what is the cost to go from 2 to n or 3 to n, or if you know the cost to land at n minus 2 and land at n minus 1, in both of the ways we can figure out the problem, right? But my point being that here, if some pre-computation is already done for you, if someone can already help you, or if you can delegate the task to someone to figure out something for you, you will be able to very easily get your final answer, right? Because you already have the most optimal answer up till here, and the most optimal answer up till here, the only choices you have are two from here, right? Two choices from here, or you can say two choices from here, right? So I'll consider this as approach 1, and I'll consider this as approach 2, right? Using both of the approaches, we'll try to solve the problem. Now let's try to consider approach 1. If you consider approach 1, then let's say if I write a function f that takes a parameter I and tells me minimum cost to reach nth stone from ith stone. Okay, we can say it like this, that what is the minimum cost to reach the nth stone from the ith stone, because if you see, if I consider I is equals to 1, then it tells me what is the minimum cost to reach from 1 to n. Can I say that? I can say f of 1 will tell us the final answer, right? If I am somehow able to successfully implement this function recursively, then if I will call f of 1, then can I say that f of 1 will give me the final answer, because the final answer that I want to compute is the minimum cost to reach from 1 to n, and this is giving me cost to reach from any ith index to n, right? So I will be able to get my final answer if I'm able to implement this, and then from our main I will call f of 1, right? So how can you implement this? I am saying I don't know how to implement f of I, but I can say that if somebody can do some assumption for me, right? So we will assume that the function f works correctly for I plus 1, that is, correctly calculates minimum cost to reach nth stone from I plus 1th stone. And one more assumption you need, f of I plus 2, that is, correctly calculate minimum cost to reach nth stone from I plus 2th stone. See, we did the same thing, right? We wanted to calculate f of 1. If somehow somebody can give you f of 2 correctly and f of 3 correctly, that is the minimum number of, or I would say minimum cost to reach from 2 to n and minimum cost to reach from 3 to n, then what I can do? I can say I will add absolute value of hi minus hi plus 1 here. I will also add hi minus hi plus 2 here, and then calculate the minimum of it. This expression resolution is going to be our self work, right? That is, somebody gives you that from any ith stone you can just go to I plus 1th stone or I plus 2th stone. So if somebody gives you that from I plus 1th stone in what minimum cost you can reach n, and from I plus 2th stone in what minimum cost you can reach n, if this is already given to you, then I know that from the ith stone I can just reach the I plus 1th stone in this much cost and I plus 2th stone in this much cost. So if I add these two costs and add these two costs and calculate the minimum of them, I can get my final answer, right? So what I'm trying to say is, from the ith stone, we go to I plus 1th stone, we go to I plus 2th stone, right? Now somehow we know that in what minimum cost it can reach n, let's say x, in what minimum cost with what number of ways it can reach n, this cost is y, then in order to reach I to I plus 1, we need hi minus hi plus 1. And now to reach from I plus 1 to n, we need x. So I'll add these two. And then to reach from I to I plus 2, I can do hi minus hi plus 2. And then I plus 2 to n, we can do y. So we'll add these two. And now this is one particular path, or I would say this is one particular way. This is another way. So what is the minimum of both the ways? I will just get that. So I'll get the minimum of both the ways. This is what I'm trying to do. So you can see this recursive relation can help us to implement approach number 1, right? And don't you think this looks like a lot like Fibonacci? Because like reverse Fibonacci kind of a thing, where ith term is dependent on I plus 1 and I plus 2th term. In Fibonacci, the ith term is dependent on I minus 1 and I minus 2th term. But when I will write approach 2, it will become exactly like Fibonacci. Let me show you. So if I write approach 2, if I say f of n, let's say there is a function f of n, and we say that minimum cost to reach nth stone from first stone. Okay. If let's say f of n gives you the minimum cost to reach the nth stone from the first stone, then I am going to do some assumption. I will say that if someone can give me f of n minus 1, what is f of n minus 1? Minimum cost to reach n minus 1th stone from first stone. So let's assume correctly calculates this value. Our function correctly calculates this value, right? That from the first stone, in what minimum cost you can reach the n minus 1th stone. Let's say our function correctly calculates this. We are going to assume that. And f of n minus 2, that is correctly calculates minimum cost to reach n minus 2th stone from first stone, right? That is, what is the minimum cost to reach from the first stone to n minus 2th stone? If somebody can give me these two values already, then I can say that to reach n, I can jump from n minus 1 to n, and the cost incurred will be h n minus 1 minus h of n absolute value. And if you go from n minus 2 to n, the cost incurred will be h n minus 2 minus h of n. And now among these two costs, we have two different paths that I can reach n via n minus 1, or I can reach n via n minus 2, considering n minus 2 was the second last index or n minus 1 was the second last index. I will just calculate minimum of these two expressions. Minimum of these two expressions, right? And that's it, right? And this is what I want to say, that either you can reach from n minus 1 to n, or you can reach from n minus 2 to n. Minimum cost to reach from 1 to n minus 1 is, let's say, x. 1 to n minus 2 is, let's say, y. Then to cost to reach from n minus 1 to n is h n minus 1 minus h of n. And here is h n minus 2 minus h of n. So if I add these two and I add these two and calculate the minimum of the two, then I'll be able to get the minimum of the two different paths from which I'm bringing my answer. And that's it. And now if you carefully see, this expression though is like 90% same as Fibonacci. F of n is equals to f of n minus 1, f of n minus 2, some computation with f of n minus 1 and f of n minus 2. So it is very close to what Fibonacci actually gives us. Can I say that? Right? So based on any one of these two approaches, we can write a recursive relation that can actually help us to figure out the solution to the problem, right? Now let's try to do a simple dry run, okay, with an example. So let's take 10, 30, 40, 20. Okay. We have 10, 30, 40, 20. Okay. Let's go with approach 1 first. Let's go with approach 1 first. Let's say this is stone number 1, stone number 2, stone number 3, stone number 4. Okay. Now, I say that in approach number 1, what did I say? I say my final answer is going to be f of 1, right? So I'm going to call for f of 1. I'm going to call for f of 1. What is f of 1 going to say? F of 1 will tell me minimum cost to reach from 1 to n. That is my final answer, right? This is my final expected answer. Okay. Now I don't know how to go from 1 to n. So what did I say? I will say that just go and calculate minimum cost to reach from 2 to n and minimum cost to reach from 3 to n. Okay, I'll just go and calculate minimum cost to reach from 2 to n and minimum cost to reach from 3 to n. Okay, this is something that I'll calculate. Now I don't even know what is the minimum cost to reach from 2 to n, to be very honest. I don't even know this, right? So what I'll do, I'll say I don't know how to go from 2 to n, but I know I can go from 2 to 3 or I can go from 2 to 4. So what is the minimum cost to reach from 3 to n and what is the minimum cost to reach from 4 to n? Just give me that. Similar thing here. What is the minimum cost to reach from 4 to n? What is the minimum cost to reach from 5 to n? Now, technically speaking, fifth index doesn't exist, right? The fifth index doesn't exist. So this call doesn't make any sense. This call doesn't make any sense. So we will not make this call. Okay, cool. Now, f of 4, if you see, f of 4 is a base case. Now you are standing at the fourth, I would say, stone. If let's say your frog is already at the fourth stone, in what minimum cost you can reach the fourth stone? You don't need any cost, right? So if I becomes equals to n, then your cost is 0. Because you don't need to make any jump, right? You don't need to make any jump. The cost is already 0. So this is something that we already know the answer for. This is 0. This is 0. Okay. Now here also f of 3 will call f of 4. And f of 4 will return a 0. Okay. Cool. So now if f of 4 returned a 0, what is the cost of f of 3? F of 3 cannot go to f of 5. Can I say that? F of 3 cannot go to f of 5. Okay. So the minimum cost is going to come from f of 4 only. That is, what is the cost from reach? What is f of 4? Cost to reach from 4 to n. The cost to reach from 4 to n is 0 plus. What is the cost to reach 3 to 4? The cost to reach 3 to 4 is 40 minus 20. Can I say that? So I'll say, what is this going to compute? The cost to reach from 4 to n plus the cost 40 minus 20, that is to reach from 3 to 4. This becomes 20. F of 3 is going to return 20. Right? Same thing here f of 3 will do. The cost to reach from 4 to n is 0 plus the cost to reach from 3 to 4 is 40 minus 20, that is 20. It is going to return 20 from here. We are at f of 2. We are at f of 2. F of 2 got the answer from 4. That the cost, let's say minimum of. Now here we can do minimum because we have 2 branches, right? In f of 3 we were having only 1 branch. Cool. Now I will say the cost to reach from 3 to n is 20 plus cost to reach from 2 to 3 is 30 minus 40. What is 30 minus 40? 10, comma. The cost to reach from 4 to 4 is 0 plus cost to reach from 2 to 4 is 30 minus 20, 10. What is the minimum of this? This is 30, this is 10. Minimum is 10. I'm going to return 10 from here. Now just think about it. We are back at f of 1. We didn't know how to reach from 1 to n, but now I know that how in minimum cost you can reach from 2 to n and how in minimum cost you can reach from 3 to n. What will be my final answer? My final answer is going to be this. My final answer is going to be minimum of. What is the cost to reach from 2 to n? It is 10 plus cost to reach from 1 to 2, that is 10 minus 30, 20, comma. What is the cost to reach from 3 to n? This is 20. And what is the cost to reach from 1 to 3? This is 10 minus 40 absolute value, that is 30. This is 30. This becomes 30, this becomes 50. What is the minimum of 30 comma 50? It is 30. 30 is your final answer. Right? So see, we went along and calculated the minimum cost to reach from 2 to n, minimum cost to reach from 3 to n, and once I have the minimum cost to reach from 2 to n, so minimum cost to reach from 2 to n was 10, and I have the minimum cost to reach from 3 to n, this is 20. Then I can say that, okay, I know that if I would have started my journey from 2 and wanted to reach n, this was my minimum cost, and if I started my journey from 3 and reached n, this was my minimum cost. Then if I'm starting from 1, in one jump I can reach 2, so I will just add that much cost to the minimum cost of 2 to n. And or I would say that another choice is I can make a jump directly to 3, that will get added to the cost of 3 to n, and then whatever is the minimum of these two path. See, there are technically two paths. Below this, more path comes up. But whatever is the minimum of this path and this path, right? Minimum of these two paths is going to be my final answer. So this is going to be the dry run with respect to what? With respect to approach number 1. If I want to implement it using approach number 1. Just for a corner case, if you get something like this, where you reach something beyond n, then you can just return infinity, right? Or you can just say I will return infinity, right? You can either handle that, or you can even try to avoid making this call. You can even try to avoid making this call, right? Any kind of, like, that is going to be a syntactical sugar that we can do in order to implement. Now if I see the same to same thing with respect to approach 2, that was in reverse direction, 10 30 40 20. I say that I want to calculate f of 4. That is, what is the minimum cost to reach from 1 to 4? I don't know what is the minimum cost to reach from 1 to 4, but I can say that if someone can give me the minimum cost to reach from 3 to 4, or someone can give me the minimum cost to reach from 2 to 4, then I can maybe calculate something. Now I don't even know this. So I'll say, if someone can give me the minimum cost to reach from 2 to 3, and someone can give me the minimum cost to reach from 1 to 3. Same thing here, if somebody can give me the minimum cost to reach from 1 to 2, because 0 doesn't exist. Okay, 0 doesn't exist. F of 0 will not work for us. Okay, cool. Now same thing here for f of 2. Okay, cool. Now what is f of 1? F of 1 is the base case, right? What does f of 1 means? F of 1 means that from the first index, in how much minimum cost you can reach 1? Can I say 0? Everywhere this is just going to immediately return 0, because from 1 to 1 is the starting point. How much minimum cost you need in order to reach from 1 to 1? It's technically nothing, right? It's 0. So that's this case. Now we are back. So from here, so how the calls are going to be, this is going to call here, this is going to call here, this is going to call here. It's going to return 0. Now we are at f of 2. Now I know what is the minimum cost to reach from 1 to 1, and what is the minimum cost to reach from 1 to 2. We know that. So we'll say 10 minus 30 plus 0. What is 10 minus 30? 20. I can say return 20. So the minimum cost to reach from 1 to 2 is 20. Now we are at f of 3, because when f of 3 will call f of 1, it will immediately return 0. We are at f of 3. Now f of 3 knows what is the minimum cost to reach from 1 to 2, and what is the minimum cost to reach from 1 to 1. What I'll do, I'll calculate minimum of. The minimum cost to reach from 1 to 2 is 20. And to reach 2 to 3 is what? 30 minus 40, 10. Minimum cost to reach from 1 to 1 is 0, plus minimum cost to reach from 1 to 3 is 40 minus 10, 30. Right? So technically, both of them are returning what? 30, 30. Minimum is going to be 30 only. We are at f of 4. F of 4 will call f of 2. F of 2 will call f of 1. F of 1 returns 0, 0. What is f of 2? F of 2 will say that minimum cost to reach from 1 to 1 is 0, plus minimum cost to reach, or like only cost to reach from 1 to 2 is 20. So I'm going to return 20 from here. Now you are at f of 4. Now this is where you started. Now you know what is the minimum cost to reach from n minus 1 to n, and what is the minimum cost to reach from n minus 2 to n. What is going to be my minimum cost? It will be minimum of. Minimum cost to reach from 1 to 3. 1 to n minus 1, that is 1 to 3 is 30, plus cost to reach from 3 to 4 is 20, comma. Minimum cost to reach from 1 to 2, 20, plus cost to reach 2 to 4 is 10. Minimum of these two values is 30. 30 is my final answer, right? So even using approach 2, we are able to get this. Why? Because all I want is, we have two cases. With respect to f of 4, I just know that there are two cases. Whatever is the minimum of this case or this case, this case or this case, whatever is the minimum is going to be my final answer, right? So you can see how gracefully we have implemented the solution, that both of the approaches are converging to the same thing, right? In this case, the base case is going to be, if I becomes equals to 1, I'm going to return 0. That's it. That's it, right? So this is how you have to manipulate your solutions. This is how you have to manipulate your solution recursively. You have to assume that what is the bare minimum you can do. If I think in that term, self work, base, recursive approach and base case, then self work should be your bare minimum task. If you're standing at n, the bare minimum you can do is check n minus 1 and n minus 2, because from there only you can reach n. Or if you see in forward direction, if you're standing at I, the bare minimum that you can do is go from I to I plus 1 or I plus 2. You cannot do more than that. And that is not even required. Can I say that? Based on that, you can write any of the two recursive solutions and that are going to work for you. I hope this basic dry run of the recursive relations that I wrote in approach 1 and approach 2 is clear to everyone. So let's start the coding implementation. Okay. So first of all, I'm going to code my approach 1. I'll say that I need a function f that takes a value n. Okay, why int f? Because it is going to return us the minimum cost. Returns the minimum cost to reach nth stone, or I should say int I, right? To reach nth stone from ith stone. Okay, cool. So I can say that my answer is going to be what? Return minimum of f of I plus 1, that is minimum cost to reach from I plus 1 to n, plus absolute of, there is going to be a heights array, right? Int star heights. We also need to pass this heights array. You can even make this array global. If you somehow make this array global, right, then you will be able to see your coding solution to be exactly like this. Okay, so let's do one thing. Let's keep a vector here, right? I want to keep my recursive solution clean so that you can correlate with that more easily. Okay, so I'm making a global vector for the timing to keep the implementation clean. Okay, and let's say it as h. This is going to store heights. So I'll say absolute of. Now if you are making a jump from, if you know that in how much minimum cost you can reach from I plus 1 to n, then technically you are going to make a jump from I to I plus 1, right? So I'll say h of I minus h of I plus 1. This is the first approach. Second is what? You can go from I to I plus 2, and if somehow you know the minimum cost to reach from I plus 2 to n, then I'll say I'll just add the cost of jump from I to I plus 2. That's it, right? That's it. We'll do hash include math. Okay. So we are going to include the header file math.h, right? And let's see if there will be any error. We'll try to figure it out. Let's try for base cases. Base cases say that if I becomes equals to h dot size, that is n. Okay. This is the case when I becomes equals to n. In that case, the cost will be 0, right? We don't need any cost to jump from n to n. Okay, cool. Also, can I say that one more corner case we have to write, that if you are at the second last, h dot size minus 1, that is we are at the second last stone, then I can make only one jump from here, that is to I plus 1, right? That is to I plus 1. So I can say my answer is going to be just directly this. My answer is going to be just directly this. Okay. That if you are standing at the n minus 1th stone only, right? That is the second last stone. Then from there you can make a jump of 1 only. You cannot do anything beyond that. You cannot do anything beyond that. This is something that you can do, right? Otherwise, every time you will be able to make 2 jumps. Otherwise, every time you will be able to make 2 jumps. Okay. So we can say that int n std c in n, and let's say we can resize our vector. So we'll say h dot resize to be n, right? Or if we don't even want to do resize, we can just do pushback. Int I equals to 0, I less than n, I plus plus. Int x, let's take the input of the height. We'll say h dot pushback x. Okay. And just to make it one based indexing, to make one based index, I will do h dot pushback 0, right? On 0th index, we store dummy value, right? Just to make the implementation simple, right? That's why I'm doing, although you can handle it in a more graceful way also. But for the timing, I just want to keep the implementation simple. At last, I will say just call f of 1. F of 1 is going to be my final answer, right? That's it. This is going to be the simple coding implementation for our approach number 1. Cool. Also for min, I believe we should try to have the algorithm file. I guess it's implemented there. Okay. We can check although, but I believe in hash include algorithm, we should be able to find min. Okay. Cool. Let's try to run this code. Okay, it doesn't find min. Let's see in what file we can find min. So actually, I did make mistake. We need to do std min, right? That's the mistake, I guess. I guess now we don't need algorithm. Looks fine. Now it's going to expect some input from us. So let's do one thing. Let's change our configuration to terminal so that we can give user input. So let's try to run the code directly here. So we'll say g++ proccjump.cpp minus o run. Everything compiled /run. So we are going to give a 4 length array, right? So the length of the array is going to be 4, and the array is going to be 10, 30, 40, 20. Okay, we are computing the answer as 50. So that's the wrong answer. The answer should be 30, right? So let's try to debug what is the issue. So now the array is 1 based index. So technically the length of the array is what? N plus 1, right? So let's do one thing. So this n is going to be there, right? Because I created a dummy array. I added a dummy value 0, and then beyond that I'm adding 10, 30, 40, 20. So when I will be compared, I need to be compared with 4, right? Whereas h dot size is what? 5, right? So let's do this. So we will say h dot let's pass n here. We can pass n here. One parameter we can manually pass. So in every function call, we need to just pass n, and let's compare it with n. Okay, let's try now. This should also be n. Okay, so I'm passing n so that I just directly compare it with n, because in this case the n will be what? 4, right? So 0, 1, 2, 3, 4. So when we reach the 4th index, we can do that. Or you could have done h dot size minus 1 also. That could have been done as well. Let's recompile. Here also we need to pass n while calling. Okay, let's recompile. Okay, compilation done. Let's run 4, 10, 30, 40, 20. Okay, it gives segmentation fault. Let's see what happened now. So now we need to manually change h dot size here also to n, right? Because now h dot size will be what? H dot size will be 5. 5 minus 1 you are technically comparing, right? Whereas n should be comparing it to 3, right? N should be comparing it to 3 because this is the third index. So that was one mistake that we were doing. Let's try to run it again. /run and 30. So we are getting the correct answer. We can just very quickly verify with one more test case and then we'll be good to go. So for this test case, the answer should be 40. For this test case, the answer should be 40. And you can see the answer is coming as 40. I'll just get last test case. For this test case, the answer should be 0. And you can see the answer is coming as 0. So we have successfully implemented. A few changes we had to do because we converted our array to from 0 based index to 1 based index. So we had to manually pass n because just by comparing h dot size, you will get wrong indexes, right? So I hope this approach 1 implementation is clear to everyone. So based on approach 1, now I want you guys to implement the approach 2, which is more similar to the Fibonacci based implementation, right? That is going to be very simple to implement and similar kind of a base cases and all you can use. If you want, you can even convert that array also to 1 based indexed array and then make the implementation changes. But for the timing, I am not going to implement the approach 2. This is going to be a takeaway assignment for you guys to try and implement the approach 2 for the given function f.